and share the screen. Oops. Okay, so let's get started. Last time we talked about the Markov chain. So we can use Markov chain to study the joint probability, joint distribution of, for example, three loci A, B, and C uh, here along a chromosome. Okay, so if we start from A, and let's treat A as the start of the Markov chain, so we can write the probability, join the probability of A, B, and C into this way. So since we start from A, right? So we calculate, we just put the absolute probability for A here, because here we talk about the backcross design. So for any locus, we only have how many genotypes here for each locus?
Two.
Yeah, we only have two, right? Very, very good. Thank you. So either one or two, because this is a backcross. So we define uh, A1, A1 as one, right? And we define A1 and A2 as two. And they have equal chance. So that's why the probability of A equals to 1 or probability uh, uh, of A equals to 2, they are equal, and both are equal to 1 over 2. So that's why we put the absolute value probability for A here. And since this is a Markov chain, so the second step, the state of the second step only depend on the previous state, right? Previous step. So here we multiply this probability by the conditional probability of B, genotype of B given A, and so on. So because this in the third step, the genotype of C only depend on the genotype of B, not A. So that's how we describe this Markov chain. And based on this, so if we consider the transition from locus A to B, so we can use this transition probability matrix. And so this is how we define this matrix. Because at this element, so this is a 2x2 table. So at this element that represented the probability that you're going to see the genotype for A is equal to 1, and the genotype for B is also equal to 1. So what is this probability? Because this is a backcross design. So if you see A and B are both of genotype 1, that means there's no crossing over. There's no recombination between these two loci, right? So the probability should be 1 minus RAB. So RAB represented the recombination frequency. So everyone should be very familiar with this. So this is the probability that you see these two genotypes. So for this one, it's easy to understand this, right? If you see A genotype for A is 1, but the genotype for B is 2, which means the genotype for B locus is B1, B2. And if this happens, means there's a crossing over occurring between these two loci. So the probability of that is RAB. So this is the transition matrix, probability matrix from A and B, from A to B. So we can use the same strategy to define the transition matrix between B and the C, right? So because the C, the status, the state for C only depend on the state for B. So this is the Markov chain. And basically, this matrix, the transition matrix between B and C is very similar to this one. You only need to replace the RAB by RBC. Is that clear? Is that clear? So the same, but you just need to replace this matrix. So it's very similar to the transition matrix between A and B. However, you have to use the recombination frequency between B and C to replace RAB. So now, once we have this, so we can easily calculate the joint probability. Suppose you did this backcross design, and from the pool of the many progeny from this cross, you want to calculate what's the probability, what's the chance you're going to see this progeny. So what is this progeny? So you want to calculate the probability that the progeny have genotype 1 for A, but genotype 2 for B, and 2 for C. So this is a very, very typical example. And so we can use this joint probability here. So this is the joint probability, right? So we put the 1/2 here. This is the probability of A equals to 1, right? Because they are of equal chance. So we put a 1/2 at first. And this is the transition from A and B. A takes the genotype of 1 and B takes genotype of 2. So which means you're gonna look at this transition matrix and find the right element here, right entry. This is the probability of A taking the genotype 1, but B taking the genotype 2. So you use this number, which is this, right? This one here. So that's why you see here. And for this one, so from this matrix, which element do we need to select? Can anyone tell me?
One minus RBC.
Yes, because this is 2 to 2, right? So we need to look at here. So this is very similar, should be very similar to this one, but not identical. We have to replace this by RBC. So that's why we use this. Okay, very good. Any questions here? So I'm sorry, each time, so I'm not very familiar. I'm still not used to teaching the Zoom course, because once I finish a single slide, I always mess up the slides. Let me remove this notes here. And okay, so let's go back to the original. So any questions here? Is it clear how we use this Markov chain and also use this transition probability matrix to help us calculate the joint probability for any progeny of a specific genotype from this backcross design. Is that clear? Very good, very good. Okay, let's move on. All right, so because sometimes it's it's difficult to figure out which element in which transition matrix. So there's a better way to do this. So even better when we want to use computer, for example, R program to help us to do the calculation. So we're gonna use the matrix notation here, presentation here. So for example, the same example. So from the same design, backcross design, if we want to calculate the joint probability of this genotype, A equals 1, genotype 1, B equals genotype 2, C equals genotype 2. So we can use matrix calculation. So for example, so how do we represent let me see, how do we represent the genotype for one? So for locus A, so how can we represent the genotype that A equals to 1? So we use this. So we use D matrix. So this is a 2x2 matrix, and we only look at the diagonal entries here. So if we put 1 in the first entry of the diagonal, then this represent A equals to 1. So that's the way we use matrix notation to represent the genotype of 1 for A. So so similarly, so if we want to represent the genotype of 2, so we use the second diagonal entry here. So this is for locus A. So if we want to represent the genotype for locus B and C, we use the same way, right? We just change this letters here. So this is how we do this. And because to facilitate this matrix algebra calculation, so we use another useful thing. So here we use J equals to a 2x1 unity vector. So just one element 1, 1 in this vector. And so we can express this joint probability using this way. This is exactly the same with here, but using the matrix presentation here. All right. So so how do we do the calculation here? So here, the 1/2 is the same, right? Because we start the chain from A. So this, and the probability that A takes 1, genotype 1 is equal to this. And we put a unity vector here to facilitate the matrix calculation. And this is the genotype of locus A, and this is the genotype for locus B, and this is the genotype for locus C, because here A equals to 1, so that's why we use the first, so we put 1 in the first diagonal element, and the genotype B is 2, so we put a 1 here, and C 1 here. And the same here, so we put the entire transition matrix here. So this is the TAB, because you see the RAB in this matrix, right? And this is the transition matrix for B and C. And in this case, you do not need to specify which element that you need to use. For example, here, you need to find which element that you need to use for calculation. Sometimes you may make some mistakes, right? So then your calculation will be incorrect. But here, you don't have to specify which element, because these genotypes will help you to pick the right element from these two matrices. So this is an easy way to do this using the matrix presentation, and the results is identical, it's the same with this one. Questions?
I have a question. Sorry.
Yes, go ahead.
Yeah, why do we use the unity vector again, and why is it used twice?
Why do we use the J, right?
Mm-hmm. Yep.
And why do we use what for twice?
So in the third line, you see there's J complement, and also at the end there's just J.
Oh, right. So yeah, this is for the matrix calculation. So let me show you. So here the probability, the final answer for this probability should be a single value, right? A scalar should be scalar. So the use of this unity factor is try to compress the matrix into a single scalar value. So let me show you why. So this is a scalar, so that's 1 times 1, right? It's okay. But here J is a, so the prime here means the transpose. So the original J is 2 by 1, but if we transpose, so the J prime should be a 1 times 2, right?
Yes.
Okay, so let's put 1 times 2 here. Oops, oh, it's hard to do this. Okay, and how about this? D is 2 times 2, right? And this is also 2 times 2, right?
Yes.
Okay, and this is also 2 times 2.
Yes.
2 times 2. Yes. And 2 times 2.
2 times
and okay,
1.
Now this is 2 times 1, right?
1.
Okay, so suppose we do not use J prime and J. So what happened is like we cannot do this matrix calculation correct because 2 times 2, 2 times 2 here, this calculation gives you a matrix of 2 times 2. So you can never be able to get a scalar value for this probability. So because the unity vector will not change your calculation because they are 1, right? But they can help us to change the dimension of the calculation.
Oh, okay. Yes.
So by using this prime, J prime here, and put the J at last, you can transform the matrix into a single value scalar.
Okay.
That's a perfect number for this.
Okay, got it. Thank you.
Sure. Any other questions? Okay, let's move on. Okay, so I will not spend time on this slide. So this gives you some very basic idea about the matrix presentation. And please, yeah, after the class, please look for some stuff online, like Dr. Google, so you can find a lot of useful things to help you to refresh your memory or knowledge about the matrix calculation. This is important because in the final exam, I may ask you, I will not give you a very complicated calculation, but I may ask you to use R to write something very simple. Let me show you. So let me show you example here. Stop share here. Okay. Okay. So this is an example to show how you can use R to manipulate a matrix, to use matrix to help you to do the calculation. So so for example, we can first define a matrix. So this is we put so we want to generate. So this line actually help us to, in R. So help us to generate a matrix A in R. This matrix is a 2 by 2 matrix, so that's why we put 2 here. Can you see my a pointer here?
Yes. Yes.
Oh, okay, good. So we have two here to define the dimension of this matrix A, and we will put these 4 numbers in the matrix using this order. So by row means I put by row equals true here means like these four numbers will put in this order. So it will fill up the first row and the second row. So if you look into this matrix, you will see A is like this. So the first row is 1 and 2. We fill the first row first, the first two numbers, and then second row, right? So you can do the same thing. So to generate a B here, so you put 5, 6, 7, 8 into another matrix of 2 by 2. And also the order to fill in this matrix is by row. So 5, 6 here and 7, 8 there. So you can, when we do the plus and minus, so this is the same with the calculation using numbers. So you just put A plus B here. So it will give you the answer, because for each element here, because these are 2 by 2, right? So so you're gonna see if you calculate A plus B, so for the first element, this will be the sum of the first element of A and B. So 1 plus 5 equals to 6, 2 plus 6 equals to 8. So if you do minus, the same, right? But however, if you want to do the times or multiplication, so you cannot just say A times B. So you have to use this. So still, we put a time in the middle, but this time should be surrounded by 2 percentage sign. So this will tell R that you do the multiplication for 2 matrices. And so this is the way to do the multiplication for 2 matrices. So let me show you. Can you still see my screen, the slides? Okay. All right. So here is this is an example I presented in the lecture notes. So we have 2 matrices, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So the first matrix is 2 by 3, and the second is 3 by 2. So this is legal because 2 by 3 times 3 by 2 will produce a 2 by 2 matrix. The answer will be a 2 by 2. So let me show you how to do this. So this is the first matrix, right? We put 1, 2, 3, 4, 5, 6 into a 2 by 3 matrix like this. And this is how we create a second matrix of 3 by 2. So we put 7, 8, 9, 10, 11, 12 into this matrix, and we do the multiplication. And when you check the answer, yes. So in the lecture notes, I just calculated the first 2, and the first one is 58, and the second one is 64. So if you check your results, yes. Okay, so this is how we use R to help you do the calculation of matrices. So in the final, probably I will ask you to use this to calculate the joint probability of locus A and B and C. If I give you the type of design and the genotypes for A, B, and C, so you should be able to use the matrix calculation to calculate the joint probability using R. So yeah, don't worry. So we're gonna so after this lecture, maybe on Thursday in discussion, we can do some practice. I can show you some example to do this. All right. Okay. Cannot see the slides. Oh, sorry. Which slides, Chong? Which slides can you?
Oh, I just when you show you ask see if we can see the slides. At that time we cannot see the slides. I only can see the R scripts.
Oh, you only okay. So
yeah, but I think that not.
You got it. Okay.
Problem.
So
yeah, I get
didn't
it.
miss anything, right? Okay.
Yeah.
Good. Okay. Yeah. So sometimes I didn't pay much attention to the chat box. So if you, yeah, you can type in. So if you do not see my response, just turn on your audio and let me know. So if you have questions, problems. Okay, where is it? Here. So now you can see my slides, right? Okay. Oops. Why you cannot? Sorry. Give me a second. Okay. All right. So last time, last Thursday and just now we talk about what design. We talked about what design. Backcross, right? That's a simple one. So we always started from the simple one. Now we will talk about some complicated one. So F2, all right? Because backcross we only have like two genotypes for each locus, but now for each locus we have 4 possible genotypes. Then a 2x2 transition matrix is not enough, right? It's not sufficient. So we have to generate a larger, bigger matrix here. So this is how we define a transition matrix from A and B, from A to B in a F2 design. So the same, the probability of A and B and C will be defined in the same way, because this is also a Markov chain. We start from A, and the second step, the state of the second step only depend on the state of the first step, and so on, right? But here, the first thing which is different from the backcross design is here. So so in the backcross design, we put a 1/2 in front, because that's the probability of A, right? Either the A equals to 1 or 2, so the probability should be 1/2. But here, because A can take one of the 4 genotypes, so this number should be changed into 1/4. Is that clear? Okay. Now, because of the complication of the genotypes involved in at each locus, so we need to use a 4x4 table here to represent the transition probability matrix from A and B. So now we are expert now, so I don't need to explain why this number should be like this, right? So this 4x4 table here. By the way, so in the final, I'm ask you to create this table for me. So you should be able to do that, right? In the final exam. All right. Now, so this is a 4x4 table. Actually, because F2 is a advanced backcross, so a more complicated backcross, and it's actually the backcross square. So you can see the relationship between this. So this is a transition matrix for the backcross design, and if we square this matrix using this is another matrix operation, the Kronecker square. So just like so just now I showed you the dot product of matrix, but here this is another operation called the Kronecker square. So so when we square this matrix, you will get exactly the same thing here. So this is too complicated. It's not required. I just for your own knowledge, I just show you what's the relationship between the transition matrix AB in the backcross design with the transition matrix AB in the F2 design. So this is the relationship. Okay. All right. So now we have the transition matrix AB here, and the same, right? So if we want to construct a transition matrix for BC, so almost identical, but for this one, you have to replace the RAB by the RBC here. So to define your matrix for the BC. Also 4x4. And we use the same joint probability calculation. So this is the Markov chain, right? Transition. And here, now you understand why we put 1/4 here rather than 1/2, right? All right, so for example, the same example here, so we can calculate this. So for this one, you need to figure out 1, 2. So this is the thing you need to use for this. And 2 to 3 is 2 to 3 should be similar to here, but you need to use the RBC square, right? So for this one. So this is why you can get this answer. Any questions?
Yes. The B, so you said we need to use, oh, of course we need to use BC, but it's going to be in the same position.
Yes, same position. That's correct.
Okay.
Yes.
Okay.
Very good. So because I didn't provide the matrix for BC, right? Yes, the TBC should be very similar to the TAB, but you have to replace RAB by RBC. So, and then that's why you see here, right?
Yes.
Okay, very good. Any other questions?
Yes. What is the value 3 in this case?
Oh, 3. So 3 means good question. So let's go back. We have 4 genotypes here, right?
Okay.
So for BC, we only use 1, 2, but here we use 1, 2, 3, and 4.
Got it.
Okay. Any other questions?
I have a question. Yeah. So in these slides, you see TAB, the follow TAB is equal to the upper TAB, but for the later one, it's a 2x2 matrix and a multiply 2x2 matrix. But the result is 4x4.
So okay, so if you just look at here, 2x2, this is the TAB. Let's put a TAB prime here. So that's for the back cross, right? So this thing, if you put a square here, that's equivalent to this operation, and this will gives you this. So this is not required, but I can show you why is this. So this operation means what?
Oh, okay, I got it. So it's not multiply, it's not times.
No.
Okay,
yeah. So this is called the Kronecker square. So it's not the thing I just showed you. So in R, I showed you the basic multiplication, but this is not. So what?
Yeah,
how do we?
I see. It's like so in biology, it's like TAB. There is a like the progeny of TAB, and the column is so I can how to see that.
Yeah. So actually, this is the same with the so if you look at this dimension, so this is one parent 1.
Yeah.
And this is parent 2. The same thing, right?
Yeah. See, okay, got it.
And that's why you can generate this, 4x4, 16 stars.
Okay.
Yeah. All right, good. Okay, now you feel comfortable with this, right? So yeah, definitely I'm gonna put something like this in the final. So first I'm gonna ask you to define this matrix, and then I will give you some progeny with a specific genotype, and you need to calculate that probability for me using the transition matrix defined by you. Okay. All right. So So let's go back to Ryan's question. So yeah, here we have 4 genotypes. So that's why we put 1, 2, 3, and 4 here. But for F2 design, actually, the 2 and 3, so if we do not know the haplotype, we just look at the genotype. So these two actually cannot be distinguished from one another. So these two types of genotypes, 2 and 3, are always mixed up. So you cannot tell which is which. All right, this is why we said, okay, in practice, in reality, so the genotype 2, number 2 and number 3 cannot be distinguished. All right. So for example, if we want to calculate the probability for this progeny, so this is an example. This could be a case problem that I can put on the final exam, right? So if you look at this genotype, so if you look at the locus A, so that's clear. That's what number in F2 design genotype. That's 1, right? So for F2, so we have 4 genotypes. If we look at the first locus A, so because A1, that's the first genotype, so we put 1 here. But for here, the B locus, it could be A or it could be 2 or 3, right? The same for locus C, could be 2 or 3, because we don't know, we cannot distinguish the genotype number 2 and number 3. Is that clear? So for this kind of ambiguous situation, ambiguous genotype, so we denote the genotype for locus B as this. So it could be it could be 2 or 3. So we put a parenthesis 2, comma 3 here. So the same. So we use this to represent the genotype for locus C, because we don't know which genotype there actually are. Yeah, they could be number 2 or number 3. So now if we want to calculate the probability of this, so we have to consider for B locus, we have to consider 1B equals to 2 or 1B equals to 3, the same for locus C. So because the genotype, let's look at the B, locus B. So the genotype of 2 and the genotype of 3 are mutually exclusive, right? So if genotype takes, if B equals to 2, it cannot be the 3 for any progeny, right? So these two events are actually mutually exclusive. So in statistics, in probability theorem, so we have to add up these two probabilities. That's why you see this sum here, right? Sum here, right? So we have to consider both situations. So because those 2 or 3, those are the mutually exclusive events. So we have to add up the two probabilities to calculate the union of these two events, and the same here. Any questions? So for this situation, so this is the answer for this genotype, the joint probability for this genotype. Any questions?
What are the numbers next to this, on the sum symbol again?
Let me see.
3 and K.
You mean
3?
this number?
Yep, that's it.
So, okay, because here, because if we knew this is 2, not 3, so here we don't do the sum, we just calculate when K equals to 2 for the locus B, right? Right? But because if we see this genotype, this could be 2 or 3. So, and because 1B equals to 2 or 1B equals to 3, these two events cannot both occur within a progeny, an individual progeny. Is that correct? For a single individual, you cannot take both. So that means like these two probabilities should be added up to calculate the union of that, right? So these two events are mutually exclusive. So this is in the statistics. So that's why you see this summation sign here. So we want to add up these two. So k equals to 2 and 3. So maybe I didn't get your question. So do you ask the meaning for this?
Yes. So
Okay.
we're just assuming 2 for
All
picking
right.
number, and then 3 is the total possible number of.
No, actually here. So here means like so for example, this is a function of k. Okay. This gives you a number, right? K could take like 1 or 2 or 3 and 4 values generally, okay? But here we want to consider the fk, the sum of fk, when k only take these two numbers. So this means what? This means if we do the summation from 2 to 3, from 2 to 3, so this gives you this, f k equals to 2 plus
Okay.
if k equals to 3. So
Okay.
here we only, so the summation start from 2 to 3. So here we only add up these two numbers. The same thing here. So in another way, so if we want to calculate the summation k equals to 2, starting from 2 to 4, this gives you what? This gives you three things, right?
Yep.
F2 plus F3 plus F4. Is that clear?
Yep.
Okay. So here, actually, we only use 2 and 3. Okay. I hope it's clear. So any questions? Other questions? Any other questions for this? So this is a little bit tricky because here we introduced, we put in some uncertainty here, right? Because in reality, so if you look at, if you have genotype like this, so it is ambiguous. So that's why we put both genotypes, possible genotypes here. All right, let's move on. Okay, now matrix presentation. So because we like to use this because this can help us to write code in R and to use the nicely designed matrix presentation to do the calculation. And you do not have to go back to the transition probability matrix to specify each element that you need to use, because this matrix can help you to pick the right things. Otherwise, yeah, if you do this selection from the matrix multiple times, so it's likely for us to make some mistakes. So, all right. Okay, now, so how do we denote the genotype for A equals to, so if the A equals to 1, which means the first genotype, right? So here we use a 4x4 table diagonal matrix. Sorry, we use a 4x4 diagonal matrix to represent the genotype for any locus. So let's look at the A locus. So if A takes the first genotype, we just put the 1 at the first diagonal element. So if A takes the genotype either 2 or 3, so in this diagonal matrix, we put 1 here and 1 here, which means, yeah, for this genotype, it could be number 2 or number 3. And so if A equals to the fourth genotype, which is A2 and A2, so that's very clear, right? Because so this is not ambiguous anymore. So it's very definitively defined. So we put 1 here. Any questions here? Now we can use this matrix presentation to calculate the probability, joint probability of A, B, and C for any progeny with any specific genotypes here. Now J becomes 4 times 1 vector of unity, right? So this is the using of J and J prime here is to help us correctly calculate the matrix algebra. And here 1/4. So why is 1/4 here? Why is 1/4 here?
Because there are 4 genotypes.
That's correct. Yeah. We start from A, right? A could take any of these 4 genotypes. Yeah. And also, so let me ask you a question. So this is a challenging question. So because for this specific calculation, A takes the first one. So that's why we put 1/4 here, right? If A equals to this, what shall we put here?
Is it 1/4 plus 1/4?
You mean 1/2, right?
Right, yeah.
Yeah, direction, the direction of your thought is correct. But here, the right answer is 1/4 again, because here we'll pick up this. So, because the genotype of the matrix, so this is the DA, right? So this shows the genotype for that. So if A equals to A1 and A2, so this matrix will take this form. So you have 2, 1 here, and this will pick up the ambiguity of this genotype, and still we use 1/4 here. But yeah, very good, very good. Is that clear?
That one's not quite clear. So the ambiguity of the middle genotype matrix, that okay. So now instead of, so if this, I mean,
So,
it's
yeah,
just
go ahead. So for example, if I want to calculate the probability of A equals to, A equals to 2 or 3, right? And B equals to 1, and C equals to 1 again. Okay, which means like the A locus is 1, A1, A2. Let's put 4 here. B locus is B1, B1, and C locus is C2, C2. So if we want to calculate this probability, so we still use this formula here, but why we do not use, because this actually represent 1/2, right?
Yes.
But why we still use 1/4 in this matrix, in this calculation here? Because
we know there are 4 possible genotypes, but we cannot discern 2 of them from each other.
yes, because actually the probability that A takes this genotype is 1/2, but here we put, so when we specify the genotype for A, right? So we will use this matrix, right? This will sum this 2, and this, each one of this will multiply by this 1/4, and the sum of that will be 1/2.
Okay, I get it.
Got it? So yeah, we do not have to change this number here, but this genotype matrix will help us to pick up the right thing. So the right probability. So that's the beauty of using the matrix.
I got it. Thank you.
Okay, Cool. Any other questions about this? Yep.
So what if the A progeny is not equally distributed? So like for A1 is equal to 1 over 4, and other is not equally distributed. Which
mean,
number?
So we're going to talk about that. So that's a very, very special case. So when so the genotypes, so the alleles when we show some like a dominance or recessive relationship, and if your sequencing technology cannot distinguish this molecular difference, and then so we need to use different D matrix to denote the genotypes. Yeah, very good. So we're going to talk about that later. So any questions about these slides here? Okay, very good. All right, now this is a very special design called the four-way design. Four-way, 1, 2, 3, 4. Four-way design. So if you look at the design, so we start from 4 parents here. So in terms of a single locus, there are 4 alleles, actually. There are 4 alleles, A1, A2, A3, and A4. Each parent at this locus are homozygous for one specific allele. And the first F1 is A1, A2 heterozygous. And the second F1 parent is A3 and A4. So if we do this cross, it will generate this progenies, right? So this is very beautiful because of what? Because we can clearly differentiate, right? 4 different genotypes. The information is complete. Any questions for this design? Any questions?
So unlike the previous stuff we've been working on, the information is complete here. We know the haplotypes.
Yes, because exactly. So because we know actually, so if you look at the final progeny at the 4-way design, right? So still we have 4 types of genotypes here, but we can tell the difference between number 2 and number 3 because they are different, right? All 4 genotypes are different. So we can easily, so if we check the genotype for any progeny, we can easily give a number to any progeny, either 1 or 2 or 3 or 4, because they are completely distinguishable. This is the most clearly designed experimental plan. Is that clear?
Yes.
Okay. All right, so if you compare the F2 versus this 4-way, so they're actually very similar to each other. The only thing is like the 4-way, so you can tell the difference from these 4 genotypes. But in F2, so you can only tell genotype 1 and the genotype 4, but these 2 are mixed up, right? Plus 2 plus 3. So we can say F2 is actually a special design, special 4-way design. F2 design is a special 4-way design. Okay. All right, so as I mentioned, so in 4-way, it's very clear because if A equals to 3, we knew the genotype for this locus, right? So this is very clear. So when we deal with the fully informed 4-way design, so we use very simple formula to do the calculation. So you do not see any summation signs here, right? Do you? Do you see any summation here? No, because for each locus, any genotypes is clearly defined. right? However, so let's see. So if there's some like incomplete genotype information, for example, this is a special four-way design. So the first F1 parent are heterozygous in the locus A, and it has like two different alleles. And for the second F1 parent, unfortunately, so although this parent carries a different allele, A3, but at this locus, it is a homozygous. So if we do this cross between these two F1 parents, we're gonna end up with 4 types of genotypes, right? But the 1 and 2 are mixed up, and the 3 and 4 are mixed up. Is that clear? Is that clear? Okay, now if we want to denote the genotype for genotype 1 and 2, so we still use this DA matrix, right? The D matrix, but we put 1 here and 1 here to represent these two genotypes. Is that clear? And for these two genotypes, we put 1 here and 1 here. The common thing is like for this kind of four-way design or special four-way design or F2 design, so we always use this 4x4 D matrix to denote the genotypes for any progeny. If for the fully informed four-way design, so we can use a very simple way to represent each genotype, right? But if there's if in any situation which involves incomplete information, genotype information, so we can use specially designed D matrix to represent the genotypes here. Any questions? Okay, now example. Okay, so oops, where's my pointer? Okay, pointer is here. So suppose we do this cross, and so this is very complicated. If we look at the A locus, so all right, this is identical to the previous example, right? So the first F1 parent is a heterozygous with 2 different alleles, but in the second F1 parent, so this is a homozygous with another allele. So this will give you these 4 possible genotypes. However, the first 2 mixed up, and the second 2 are also mixed up, right? Okay. Okay, so now if we want to calculate the probability of this genotype, so if you look at the first locus, so the genotype should be this. Is that clear? Because so this genotype can represent either 3 or 4, right? Because you cannot tell the difference between 3 and 4. Is that clear? Good. Okay, let's look at the second locus, B. So this is a little bit different because if you cross do this cross experiment, you will end up with these 4 genotypes for locus B. And then this time, so I believe this middle 2, these 2 in the middle are mixed up, and you can definitively define this genotype and this genotype, right? So Okay, so if the progeny, oops, it's too messy. Okay, sorry about this. So if you look at here, so this gives you the first definitive genotype. So that's why we put 1 here. It's very clear. So if you look at the C, so the same. These two are mixed up. So because, oops, I think yeah, there's a typo here. I think probably this should be 2. That's why the genotype will be like this. Oh, sorry. My apology. So see, so sometimes like, so we are too easily to make mistakes. Sorry. So this is C1. So it could be 1 or 3. So that's why for this genotype, so we use this. Is that clear? All right, so now we use the D matrix to represent the genotype. For A, because we cannot tell the difference between genotype 3 and 4, so we put 1 here and 1 here in the diagonal elements. For B locus, it's clear because there's only 1 possibility here, so we put a single 1 here. But for C, because there's an ambiguity, so we put 1 here and 1 here to represent the genotypes for these 3 loci. This is very, very important, and I hope I made it clear. So if you have questions, so we'd better stop here and pause here and make sure everybody can follow me. So any questions? Very good.
Yes.
Yes, go ahead, Ryan. Yeah.
So are we arbitrarily assigning these matrices these particular values in order to be able to discern between these genotypes that we originally could not tell the difference?
Yes, but I think, yeah, I would rather not use the arbitrarily, because this is not arbitrarily. We just, because based on this, so because we cannot, since we cannot tell the difference between 3 and 4, so we need to, so in the calculation, we need to use this summation, right? K equals to 3 to 4. So that's why we put 1 here and 1 here. So this matrix will show, okay, the possible genotype for A could be 3 and 4. So if we want to calculate what's the chance for this genotype, so we need to use the summation. So this is not arbitrary at all, I think.
Okay.
Yeah. So we just use the designed D matrix to represent the possible genotypes where the ambiguity may be involved.
Got it.
Mm-hmm. Okay. Very good. Okay, example. So here, because we use the matrix notation, right? So the D matrix actually pick up the ambiguity here, and also take care of the summation. So that's why when you use the matrix notation, you do not see the summation sign here. But here, actually, the calculation itself will do the summation for you. But when you do not use the matrix presentation, so you have to do the summation by yourself, right? Okay. All right. So as I mentioned, so the backcross design and the F2 design are actually special cases for of the four-way design. So in backcross, all right, you end up with 4 genotypes, but the first 2 are mixed up and the second 2 are also mixed up. So this is why it is special four-way design. And also if you do the F2, so this will also give you like 4 possible genotypes. However, the 2 in the middle cannot be distinguished by each other. So this is another special case for the four-way design. Okay, now, because in F2, as I mentioned, 1, 2, 3, 4 genotypes, because you cannot tell the difference between 2 and 3, right? So can we group them together? Yes, we do. So in this case, we can use a 3x3 transition matrix rather than 4x4. But I think, yeah, 4x4 is better because if you, so yeah, this is doable. So if you want to group the genotype 2 and 3 together and make a one single class, so then you can create a transition matrix of 3x3. But as you can see, this matrix is no longer symmetric. So it is asymmetrical now. This one is not equal to this one because of this ambiguity thing. So, and I think this will bring some problem when you do the calculation. So my preference is to use the 4x4 because it's very clear, right? So if you want to use the 3x3, so you have to use a 3x3 D matrix to define your genotypes as well. So this is only for your information. So this is not recommended. So I don't recommend you use the 3x3. So I prefer the classical 4x4. Any questions? Okay, now, all right. So I think, yeah. So this is about Ginny's question, right? Sometimes, like, okay, so if we look at this, probably this is a special. This is F2 design. All right, and if, for example, so imagine, so if the sequencing technology cannot help you to distinguish different distinguish the different alleles, so and in addition, there is some like dominance recessive relationship between alleles. So then, which means there's some ambiguity in the genotypes when you check the genotype for the progeny. So for example, if the A1 allele is dominant in regarding to the A2 allele, so in this case, so if you see a A1 or anything else, anything can, so the other allele could be anything. So it could take these 3 possibilities, right? So that's why we put 3, 1 here. And if you see A2 recessive individual, so that's only 1 possibility. So that's why we put 1 here. Okay. This is the dominance. So that's why we put 3 there. Is that clear? Or the other way. If the relationship, if the dominance and the recessive relationship is reversed, so you have to use a different design matrix to denote the genotypes for each individual. If missing, so this is a very terrible situation. If you do not have anything information about the genotypes, then you put this here to represent a missing genotype. Any questions? Okay. Okay, let's see. So we have 10 more minutes. Okay, good. Yeah, very good. So before I move to another topic, so any questions so far? Any questions so far? So what have we learned today so far? So we want to use the Markov chain, a very useful model to help us to calculate the joint probability of any observed genotypes for the locus A, B, and C along the same chromosome, right? Okay, so we start from the very basic design, backcross design, which is very simple. So that way, so we use 2 by 2. Everything is 2 by 2, right? So transition matrix 2 by 2, and the genotype D matrix is 2 by 2. All right. Then we, after that, we deal with a more complicated situation. So F2 design. So F2 and the backcross are actually special cases for the 4-way design, right? So in that case, we can use a larger matrix. We use a 4x4 matrix to represent the transition matrix. And we also use a 4x4 D matrix to represent the genotypes for each locus, right? Okay. And if you do not, if you hate using matrix notation, so if you want to use the very basic like numerical algebra, so you have to use the summation when you deal with the ambiguity, right? So if you like, you cannot definitively define a genotype like in the F2 design, so you cannot tell the difference between 2 and 3. So if you do not use matrix notation, so you have to do the summation by yourself, add up those two. But if you use matrix notation, so you don't worry about that, because your design matrix, your D matrix, genotype matrix will pick up the summation for you, because you put 2 ones there. The diagonal, you put 1 at the second diagonal element and another 1 at the third element of the diagonal, right? So this can simplify your calculation. So you just write a code in the R. I'm going to show you later how we can write the code in R to help you do the calculation using matrix. It's magic. It's beautiful. You're going to love it. All right. Yeah. Yeah, sounds good. Everybody are very comfortable with so far with the stuff we have learned. Okay. So, okay, conditional probability of a missing genotype using matrix presentation. So now we're dealing with missing genotype. Suppose, okay, so we still, what happened? Oh, geez. Let me stop. Sorry about this. Okay, suppose we have a chromosome and A, B, and C. Now, suppose this is a F2 design, and from this design, from this experiment, we produced a lot of progeny. And when we check just one single progeny, we got the genotype. So for example, we know the genotype we knew the genotype A for A and the genotype for C, locus C, but we're missing here. So this is missing. So how can we calculate the probability of a specific genotype for B locus based on the information we got from A and C? So this is the new topic we're going to cover. So hopefully, so I don't think I can finish this, but yeah, it's okay. So we can start, at least we can start this this topic, and then we can talk about this next time. All right, so basically we want to calculate this. So suppose we knew exactly the genotypes for locus A and locus B in a specific progeny, but we do not know the genotype for B. So, but we want to calculate how likely the B equals to 1. Okay, could be 1, right? So we want to calculate it. So based on the information we have for loci A and C, what's the probability that B will take the genotype of 1? So this is what we want to calculate. So this is the formula. Let's see how we derive this formula here. So by using the Bayesian theorem, so we can here let me see, oops. All right, so we can in this time, so we start from B and we treat B as the start point of the Markov chain. So now we can so this formula is very so you are very familiar with this formula, right? So so in today in the morning, early morning, so we talk about how we calculate the joint probability if there's no missing genotype. So we start from A. So the A, locus A is the starting point of the Markov chain, and step by step you can calculate the joint probability for A and B and C. But now since B is missing, so we can start from B. We treat B as the starting point of the Markov chain, and this Markov chain can go this way and this way. All right, so now we start from this probability, and if we go this way, so we will calculate the probability that if B takes the genotype of K, what's the probability that A will take the observed genotype here? So this is the left step, and this is the right step. So it's the same, given the B takes the genotype of K, what's the probability that C takes the observed genotype here? All right, so the same here, right? So we can use very similar the joint probability formula in the matrix notation, and the only difference is like we treat the missing locus as a starting point, so we can still use the same Markov chain probability, and this gives you this probability for just one genotype for B, right? So for example, this gives you the probability that B equals to 1 and if B equals to 1, what's the A equals to 2 or 3 given B equals to 1, and what's the probability that C equals to 4 given B to 1. So this is just one case, right? One B, when you want to calculate the B equals to 1. Now you can do the same thing for B equals to 2 and 3, 2 or 3, right? And the same. And you can also calculate when B equals to 4 and so on. So you can calculate all different values probability when B take different genotypes. And if you sum this, this will give you the all possible probability that B will take any of these genotypes. So if you use this thing divided by the summation here, the whole thing, this will gives you the posterior probability that given the information you observed at loci A and C, what's the probability that B will take a specific genotype you want? All right, so I think I'm gonna stop here for today. And so I just started this topic. This is a little bit complicated. It is almost done for this chapter, but yeah, let's continue to talk about this on Thursday. So any questions so far for today? Let's see. So any questions so far for today? No, good, very good. You guys are great. Yeah, very good, very good. All right, so if you do not have any questions, we're gonna stop here today, and I'm gonna post the recorded class to the YouTube. So in case you want to watch back, all right. And so otherwise, if you do not have questions, so we're gonna see each other on Thursday morning. All right. Thank you. Bye bye.